with the pizza. As you guys may have noticed, if you're here in past weeks, the pizza has a different crust. They actually baked it here rather than previous weeks they've been baking it elsewhere and then bringing it over. So if anyone has feedback on the crust, let me know. For those of you who've never been here before, it's the Tools and Technology Seminar Series. It's a weekly seminar to discuss tools, technologies, methodologies, either newly developed, currently in development, maybe previously developed, but just being used in a novel way or an interesting way that is of use to researchers. So today I'm pleased to present our speaker. We've got Sarah Graham, who is a grad student in biophysics in Heather Carlson's lab.
Okay, thank you. So our lab's kind of broadly interested in computational techniques for structure-based drug design. And the one I'll talk to you about today is mixed-solvent molecular dynamics. We're kind of half split into more database bioinformatics approaches, or half the lab sort of uses these molecular dynamics-based approaches. So I know everyone's maybe from a broad background. So if you're not familiar with the ways that are typically used to screen for potential drugs, there's sort of experimental or computational methods. So for example, you might be familiar with high throughput screening, where you have your target of interest and you'll screen thousands of compounds in a high throughput format using some assay. Some of the problems with this are that there's a lot of experimental variability potentially. So something that might come up as an inhibitor in one assay might not come up as an inhibitor in other assays, or even within the same assay, there's sometimes issues with reproducibility. Alternatively, there's more structure-based approaches. So for example, X-ray crystallography, or NMR, you can use to understand the structure of your protein or how small molecules might interact with your protein. But again, you're sort of limited in the number of structures that you can look at because of it's potentially time-consuming or expensive. Alternatively, there's been some computational methods that have been developed. So for example, docking. If you know the structure of your target of interest, and you have either a ligand that you know interacts with your structure or ligands that you're interested in screening if they interact with your structure. Docking methods position the ligands within the protein, and they're then scored based on how strong their interactions are. So from that, you can get an idea of how these interactions are actually occurring, or which ligands might actually interact favorably with your protein. There's also fragment-based screening approaches. So rather than looking at whole ligands and how they'd interact with the protein, sort of the building blocks of larger ligands. And I'll go through kind of one of the fragment-based approaches that you might be familiar with. FTMap is a web server that's developed that takes either protein, DNA, or RNA structures. They have 16 different small molecule probes. So they'll take each of these probes, position them across the protein surface. These are then energy minimized to identify favorable interaction sites. And then they're clustered to identify sites where these probes are making interactions within a region. Now, the reason they do clustering is there's been some initial crystallography studies where they found that regions on the protein surface that bind multiple small molecule probes correspond to what are called hotspots. So these are regions that contribute highly to the interactions between proteins and ligands. So from this, you can identify binding sites.
So this is for a given ligand and a protein get the best docking result, or just given the protein receptor, find where's the ligand binding site for arbitrary ligand.
You're asking if it can find the binding site? Is that
so is it just find a generic binding ligand, non-specific generic binding site?
Yeah, so it's a method of looking for binding sites. If you have a specific ligand that you're trying to figure out how it interacts, that would be more docking approaches that you want to use. Is that what you're asking? Yeah. So some of the strengths of FTMap, it's really fast. In their papers, they report that it's about an hour to do these calculations for a certain target. There is some time that you're sitting in their queue, potentially, because it's used as a web server. It also has a diverse number of probes, so they have 16 different types that they're using to identify a range of different interactions. However, because, or sort of the trade-off that you get in having the speed is that you're only minimally accounting for flexibility. So you can use either ensembles of structures. So if you have multiple structures from crystallography or NMR, you can use multiple structures uploaded to their server. They also have some ability for limited inclusion of side chain flexibility. what we found in using FTMap in our group, Fani was a previous grad student in our group that did uploaded a bunch of structures of proteins that had both active and allosteric sites to FTMap, and we found that FTMap tended to miss some of the allosteric sites. So this is presumably due to the fact that it's not always sufficiently accounting for the flexibility, as well as potentially a large number of false positives. So sites that are shown to have clusters of probe molecules binding there, but don't necessarily correspond to ligand binding sites. So we kind of brushed over this, but just to go into this again, we know that oftentimes in your biochem classes, you're sort of taught the lock and key model of protein binding, where there's a protein and a ligand and they'll interact. There's sort of a conformation that's already prearranged. But this isn't necessarily true. We know that proteins can change conformations to bind ligands, so this could be as simple as side chain rearrangements, where one ligand might interact with a certain conformation. The side chains would be in a different orientation in the apolyl structure and other ligand-bound structures. We also know that we can have larger motions, such as loops, that'll change conformations, or even entire domains that'll change how they're oriented relative to each other. We also know that in using some of these faster techniques, you're not truly accounting for the role of water. So prior to a protein and a ligand interacting, the protein's engulfed in a layer of water, as well as the ligand. And when the protein and the ligand come together, these water molecules either have to be displaced, and the protein and the ligand can interact directly, or some of them can be conserved in what we call bridging interactions. So these are going to be waters that mediate interactions from the protein to the ligand through an intermediate water molecule. And so our lab's been interested in developing what are called co-solvent molecular dynamics techniques. So these are techniques where you do molecular dynamics simulations, and then rather than having water as the solvent, you have a mixture of small molecule probes and water. So the general procedure, I'll go through this in a little bit more detail, but you have some mixture of small molecule probes. So essentially, little pieces or building blocks of what you would see in a larger drug-like molecule. You would then do molecular dynamics simulations, and you can look at where the probes in the water interact on the protein surface. So this addresses some of the limitations that we saw with some of the initial computational techniques. So we're accounting for flexibility. In these simulations, the molecular dynamics simulations allow for the protein to move, as well as the probes in the water to sample different orientations and conformations on the protein surface. We're also accounting for the role of water explicitly, because the probes in the water have to directly compete for binding. And from these simulations, we can map some of the favorable interactions. Now, the drawback of this, of course, is that they're potentially really time-consuming, that it becomes pretty computationally expensive to run all of these simulations. And so the method that our group has been interested in developing is, or we term MixMD for Mixed-solvent molecular dynamics. There's several groups that have been sort of developing co-solvent simulation techniques simultaneously. So you take your protein of interest, you then add a layer of small molecule probes. So in this case, I have pyrimidine shown just surrounding the protein. We then add a layer of water, and then you would do simulations. So what I'm showing you here are a piece of a trajectory that we did for a MixMD simulation of pyrimidine and water. In this case, I'm hiding the water molecules because it gets kind of tricky to see if there's sort of waters all over the place. You can see that we're allowing flexibility for the protein. You can see that there's some backbone movements. Obviously, the side chains are moving as well, but we're not showing those. And then the probes in the water are able to sample different positions on the protein surface through the simulation. So you can see that there's some sites where a probe molecule might come on and interact for a long time. There'll be other sites where the probe molecule or the water will just sort of come on and off and make a little bit shorter interactions. So once we've done these simulations, we take all of the snapshots from the trajectory and we align them. We typically use the program Amber for simulation. So within Amber, there's actually some utilities that allow you to do this. With all of our snapshots, we take them and we overlay them with a grid. So at each point on this grid, you can count up how often either a probe or a water molecule is there. So this gives you a time-averaged view of the occupancy across the protein surface. Typically, we normalize the occupancy. So we take whatever the occupancy is at a grid point, subtract the mean occupancy over the entire grid, and divide by the standard deviation. So this way, at each grid point, we'll get an occupancy in what we call sigma units, or standard deviations away from the mean. And this allows us to look at these results in a way that's analogous to crystallographic density. So you can look at them in PyMol or other visualization software and contour them at different occupancy levels.
Do you have to fix the center of mass of protein at one point?
Yeah. So there's so you just align everything. Yeah. So you would align everything. I mean, it depends how you want to do it, but you can align it at the origin. You fix the protein, and it aligns usually on the backbone carbons of the protein. And then you just align the whole trajectory. So sort of the overall goals of our MixMD simulations. First and foremost, we're interested in identifying ligand binding sites. So some of the previous grad students in our group have looked at the ability to identify both active and allosteric sites, as well as some protein-protein interaction sites. Once we've identified these binding sites, we're interested in looking at the specific interactions occurring within the site. So how can we turn the maps that we're getting into prospective models that we could use to screen for new ligands for these proteins? So just to give you an idea of what the results might look like, here I have the structure of Abl kinase. It has an active site region here that we're showing with the green ligand, as well as an allosteric site that's shown with the brown ligand down there. I told you that we're going to take the occupancy over the simulations and we normalize it. So what you'll see is that we can contour the density at different sigma values. So high sigma values are going to be sites that are very, very highly occupied. And then as you reduce the sigma values of the occupancy that I'm going to show, you'll get closer and closer to the mean occupancy. And what you'll see is that you'll start to get sort of colored blobs of density. So what these colored blobs correspond to is essentially grid points from the grid that we counted up where these probes were binding. And they're colored according to the probe type that was binding there. So for example, if you have this orange density here, that's going to be where acetonitrile was binding. The magenta is pyrimidine, or the blue is isopropyl alcohol. And typically the way, sorry, I'm going the wrong way. Typically the way that we look at this is to rank the sites by maximal occupancy. So the first site that appears at the highest sigma value, we would call site 1. As you start to get additional sites, those will be sites 2 and 3. And what we found is that the top ranked sites by maximal occupancy correspond to the biologically known ligand binding sites. So you can see that the top sites we're getting here and here are the active and allosteric sites. As you go down to occupancy that's a little bit lower, we'll start to pick up some additional sites. So for example, site 4 here, this corresponds to a protein-protein interaction site. So Abl kinase, this is actually just the kinase domain. There's additional domains. In a different conformational state of Abl kinase, what's called the closed form, there's an SH2 and SH3 domain. The SH2 domain binds right here. And there's, I believe, a tyrosine that interacts at this site. So you can see from this that we are mapping sites that correspond to biologically known or ligand binding sites. And again, as you get closer to the mean occupancy, you can see the full extent of some of these binding sites. And so initially we used to do these analyses where we'd have to load everything into PyMol or some other visualization software. You can also do it in Chimera, and manually go through the different sigma values. So we call this contouring the occupancy. And that got really tedious, and also kind of just gave you more of a qualitative viewpoint of the binding sites. So we were interested in identifying an automated way to do this, as well as giving you an analysis method that would be more quantitative. So we've developed what we call MixMD Probeview. This is a plugin for PyMol. So it's a set of Python scripts that you load into PyMol, and then you can access it and it'll pull up some pop-up menus that do the analysis. The first thing we were interested in looking at was ranking single probes. So if you have simulations that you've done of pyrimidine and you want to see how these sites rank, what you might imagine is that if you were to look at the high occupancy grid points, you might have something that looks like this, where you'll have Each grid point will have some associated occupancy. Typically what you find is that there'll be a central point that has a high occupancy, which will be the most favorable probe binding site. And then surrounding that, you'll have sites that are a little bit less occupied from the probe sampling different conformations. We needed a way to tell sites that were close together apart. And so to automate the analysis of these clusters, we've used the mean shift clustering algorithm. So this is a clustering algorithm that looks at the density gradient of points in space, so that sites that are very highly occupied become the cluster centers, and then the more sparsely occupied regions correspond to the cluster edges and are assigned to a specific cluster. One of the good things about the mean shift algorithm is that it has very few parameters to set. So it uses a bandwidth parameter. It takes a kernel density estimate of the data. This bandwidth is sort of analogous to a bin width of a histogram, where large bandwidth values would give you a smaller number of clusters, but they would be overall larger clusters, or smaller values would give you a larger number of small clusters. It's also beneficial in that it allows for arbitrary shapes or sizes of clusters, as well as not having to specify any predefined number of clusters or points per cluster. And so what this looks like when you load it into PyMol is something like this. So once we've done our simulations, we get the grid points back. Typically, we look at them in PDB format. So that's just going to be XYZ coordinates with an associated occupancy. What I'm showing you here is Abel kinase with the grid points from pyrimidine shown. In this case, I'm hiding the low occupancy grid points. So I'm only showing the grid points that are 10% of the maximum occupancy or higher. In PyMol, they have this plugin menu. You can select our MixMD Probeview plugin. It'll bring up a pop-up menu asking you what you'd like to analyze, the file you'd like to analyze, as well as putting in the occupancy cutoffs and the bandwidth. We found for our uses that 2 angstroms seem to work pretty well for clustering the data. Then you can just select rank sites, and it'll identify clusters of occupancy from your simulations. And so what I have shown here are the individual grid points. They're surrounded in this white surface that corresponds to each of these clusters. And then the sphere inside the surface is the highest occupied point. So our plugin makes this pop-up menu showing you the clusters as well as the occupancy in the cluster. And then you can step through this. So you can either click the Show Labels button and it'll show you the ranking of all of the clusters, and you could look at it directly, or you can click any of these lines and it'll highlight the different clusters, both in the screen and then on here, as well as showing you how the occupancy compares to other sites. The second thing that we're interested in doing is identifying binding sites composed of multiple probes. So typically the way we would do this is to look in PyMol for regions on the protein surface that had multiple probe types overlapping at high occupancy. And so to do this, we have a second clustering algorithm. So you can imagine that you have grid points. The different colors would correspond to grid points arising from different probe occupancies. We wanted a way to identify these. So in this case, we've used dbScan clustering, which is a density-based clustering algorithm. Essentially, it's going to look for any points that are reachable within a specified cutoff distance. So you can imagine that if you have this point and this point here, if you can connect the dots between these points, never taking a step that's greater than this cutoff, that would be the same cluster. Or points that are separated by greater than this distance, which they call epsilon or EPS, would become separate clusters. You can also specify the minimum number of points so that small clusters are removed. So for example, these small clusters would be removed, and this would become its own cluster here because it's separated from other points by greater than some cutoff distance. Again, dbScan allows for clusters of any shape or size. There's no predefined number of clusters or number of points per cluster. So the parameters that you have to set, we've chosen the minimum number of points to be 10 so that small clusters are removed. For the epsilon distance, we've used 3 angstroms. So when you're looking at the probe occupancy and identifying binding sites, you want to identify sites that are reachable within a few bond lengths. So the width of a pyrimidine is about 2.8 angstroms, or a carbon-carbon bond is about 1.5 angstroms. So using this value for a cutoff is going to identify sites that are connectable within 1 to 2 bond lengths. We're also using center of mass occupancy for the maps that we're getting, so we're only counting each of these probes over the simulation once. And so what I'm showing you here, if you take all the grid points that you've got from your simulation and you load them into PyMol, we have each color would correspond to a different probe type. Again, you would, through the plugin menu in PyMol, it'll make our MixMD Probeview plugin brings a pop-up menu. You can set your parameters and select the files that you'd like to analyze. Again, it'll assign the grid points into clusters. This then brings up a menu showing a table of all of the data for each of these clusters. So you'll see that within this cluster, there's an occupancy from each of the different probe types that you're running. And so it calculates the maximum as well as the total occupancy by summing across the grid points. It'll also give you, for each cluster, the maximum occupancy within the cluster or the total occupancy within the cluster so that you can rank them. In the same way that we have before, you can click on any of these and it'll highlight the clusters as well as show you the distribution of your clusters in either maximal or total occupancy. You can also sort by any of these. So if you're interested in, say, the highest map pyrimidine sites, you can sort by that and identify those clusters that way. So we were interested in using this, this application that we've developed for was comparing different setup methods. So our lab typically, in our setup procedure, we run each probe individually. So this would be, if you're interested in doing a simulation of pyrimidine, you would do pyrimidine in water, and that would form a set of simulations. If you wanted to do another probe, we would do a different probe in water, and that would be its own set of simulations. Other groups have done it for reasons of efficiency. They'll run multiple probes at once. So some of the other groups might do up to 7 probes at once. But it's not clear what effect this would actually have on the results that you're getting because these probes are directly competing with each other. So we were interested in seeing if both setup procedures identify the same interactions within a site, as well as if we can identify binding sites using our plugin for a range of co-solvent simulation procedures. So for this, we selected 4 different targets to use for our test. So I have Abl, kinase, androgen receptor, base, as well as dihydrofolate reductase, or DHFR. We typically do 10 simulations of 20 nanoseconds for each probe type. And then we always do a ratio of 5% probe to 95% water. So that's one of the benefits of our method, that we have a fairly low concentration of organic solvent molecules, so this could be reproduced experimentally. So in the current procedure, we have the probes listed here. In our case, we would run each of these individually, except for the charged probes, which would be run in combination. So when you're doing molecular dynamics simulations, there's a requirement that you have a balanced number of positive and negative charges. So again, with the standard MixMD procedure, we would run each of these probes individually for 10 simulations each, which would in total give you 60 simulations. We wanted to see what would happen if you're running these probes in combination. So initially we tried pairs of solvents. So that gives us 3 total solvent sets. Each of these would be run for 10 simulations each. And in each case, we're keeping the same 5% to 95% ratio of probes to water. So for example, here the ratio of probes would be split in 2. So you'd have 2.5% acetonitrile and 2.5% isopropyl alcohol. The other combination that we tried was the solvents in triplets. So 2 overall solvent sets. And again, 10 simulations of 20 nanoseconds each. In total, 20 simulations for this second combination.
If you want to do something like ammonium by itself, can you just put like chloride in there as a counter ion?
Yeah, you could. So we were interested in looking at both positive and negative interactions. So we just used, but yeah, that would be, as long as you have net neutral, that would be fine.
The beta secretase is membrane protein.
Mm-hmm.
So do you just create a water environment, or you have membrane environment?
So for base, it's just water. So there's the crystal structures just of base by itself is what we used. There's Apl structures of base we used to start the simulations.
So you only use the non-membrane portion of beta secretase?
Mm-hmm. So the first thing we were interested in looking at was to see if both of these solvent setup methods identify the same favorable interactions within each binding site. And so I'm only going to go through one set of results in the interest of time. On the left, I have the results from the simulations that were done of each of the probes individually for Able. And then on the right, I have the combinations where the solvents were run in triplet, so 3 solvents in one simulation. What you see here are the larger spheres are local maxima that were identified using our plugin, and then the surrounding grid points are all of the other grid points within that cluster. And they're colored according to the occupancy of each of the solvent types. And you can see that when these simulations are run individually, we have mapping throughout the entire ligand binding site. So I have here shown the ligands that bind within the active site of Able. However, when we run the solvents in combination, you can see that there are some differences in mapping. For example, when we run them in combination, isopropyl alcohol in blue only maps this right-hand side of the ligand, whereas when we run isopropyl alcohol in water by itself, it maps the entirety of the ligand binding site. And what happens is essentially that these other solvents are competing preferentially for binding to this site. So in some ways, this is good. You can capture the preferential interactions for the site. However, you're losing some information. So isopropyl alcohol serves as a probe to identify hydrogen bonding interactions. And so if you're not mapping it throughout this site, you're losing some of that information that you would otherwise have if you were running these simulations of each of the solvents individually. The next thing we wanted to see is if our plugin could identify binding sites for a range of these solvent setup procedures. We've also moved so I guess I'll go back to here. We've also moved to ranking by total occupancy within a region. So what we found is that in situations of combined solvents where the solvents would be competing with one another, the maximum sigma value that you would get for a site would be potentially lower because they're competing for binding to the same site. So by summing the occupancies within this region, we're accounting for that and identifying the sites with the total highest occupancy. So what I'm going to go through are the systems that we did the solvent procedures on and how we've identified the ligand binding sites. So what I have shown here is the structure of Able. The surfaces are the clusters that are identified with MixMD Probeview. In each case, I'm only showing the top 10 sites. I have the total occupancy within the site. You can see the distribution here. And then the numbers for these sites, the total occupancy within each site is shown. So you can see that for the solo simulations, we identify the active site as the site with the total highest occupancy. The next highest ranked site corresponds to the allosteric site. And then you can see that all of the other sites have a smaller total occupancy. So directly from these simulations, you can see which clusters on your protein surface correspond to the binding sites. So we did the same thing for each of the solvent mixtures. So combination A is the solvents run in pairs. You can see again that we identify the active and the allosteric site as the top ranked sites. What we find with the solvent combinations is that you get a little bit less extensive mapping. So you can see that compared to here, you're mapping the entire ligand binding surface. When we move to, solvent combinations, the mapping's a little bit less extensive. One thing we do find here is that the active site gets broken up into 2 groups. This is because these 2 clusters are more than 3 angstroms apart. But again, we're still identifying the active and the allosteric site as the top ranked sites. And again, for the third combination, we identify these sites as the sites with the total highest occupancy. So I've done this for each of the systems that we tested. Again, beta secretase, in this case, only has 1 known binding site. It's sort of a cleft across the middle of the protein. You can see that in each of the solvent mixtures, we identify the known active site as the highest ranked site. In the solvent combinations, we have a little bit less extensive mapping. So you can see here that the region that we're mapping is smaller, but this actually corresponds to the high affinity region of beta secretase's active site. So we know that there's ligands that overlap almost exactly with the density that we have there. And those are known to actually inhibit base even in animal or human trials. So again, we're finding regions of the protein surface that are biologically relevant in combined ligands. Again, DHFR, it has, again, one main binding site, and we map this as the highest ranked site in every case.
So were all of these simulations started from an APO structure or
Beta secretase and DHFR were APO structures. ABLE, trying to remember, ABLE and androgen receptor may have been ligand-bound structures. We take out the ligands before we do the simulations.
Yeah, but sometimes like a lot of these things are affected by the starting. So if you already put something large in there,
yeah,
it tends to be open. So you will rediscover the spot, but it's already open.
Yeah, so I know DHFR and base for sure were APO structures. Androgen receptor and ABLE were started from structures that had no allosteric ligands bound. Those initially came from a project we were looking at mapping allosteric sites. And then we just sort of extended the analysis with this plugin. But we have found, I've done 10, 15 different systems starting from APO structures, and we find in every case we can map the, recover the ligand binding sites.
So what do you mean by recover?
Identify.
What do you mean is the mathematical measure you say you identify?
Yeah, so the criteria we usually use comes from crystallography studies where they have hotspots of ligands correspond to sites in the protein surface that bind multiple probe molecules. So we base that on the occupancy of the probes over the simulation, and the sites with the highest occupancy would correspond to ligand binding sites.
So your site is like a hole in the protein, a pocket in the protein.
Yep, yes, either a pocket.
And the in crystallography, you have ligands binding in the protein. So what is, like, have you measured the distance between the center of your pocket, your predicted ligand binding site, and the actual ligand binding site? So all the picture you show, it makes sense, but there's no quantitative measurement to say how good is this result.
Are you essentially asking for like the percentage of the total ligand binding site? What percentage of that is kind of mapped by our probes? Is that kind of what you're?
So you give some number to show that it makes sense.
Yeah. Yeah. So I guess the numbers we focused on here would be the total occupancy within a region. I guess as far as quantifying that, we're showing the entire extent of the ligand binding site.
So for example, you have solo combination A, combination B. So which one is better? Are there any quantitative measurement I would tell which one is better?
So it depends. I guess better is a hard word because it depends what you want to get out of it.
Yes, then you need to find it, right? So if I just want to know where's the ligand binding site, or what is the coordinate, or what is the residues in the ligand binding site, which one I should choose?
I guess as far as residues in the ligand binding site, you might, it's going to be definitely system dependent. So if you might go a couple angstroms outside of these hotspots, and you could look at those residues, for instance. It just really depends on the goals of your project.
Yeah, there's like, are there any what's the distance between the predicted site and the actual site? What is the number of residues that are actually in the ligand binding site, and how many you are missing?
I don't have those numbers in here. From looking at the results, we can see that it almost exactly overlaps with the interactions that we know are occurring. But I don't have any, I guess, numbers in this presentation.
I mean, as you said, that depends on the question. So I don't say like you always need to have, but if you need a number, maybe one thing could be, say for this system, you align all the structures for which you have a ligand bound, and maybe take center of mass of all those ligands. And then you already, I think, mentioned you have center of mass for one of the clusters. So then maybe you can get a quantitative distance.
Yeah.
You would probably do it from the maximum occupant, the center of that cluster.
Yeah. No, I think his point was that how do you compare that with the known array of ligands that are already shown to bound in X-ray structure or something?
Yeah, there's been some studies by other groups where they've looked at kind of more of the degree of overlap of specific functional groups, and they've shown that these co-solvent simulations reproduce those well.
Yeah.
That might
I
be
mean,
more.
sometimes, I don't know, to me it doesn't seem like it always helps so much, because even if you say, okay, the center of masses were 2 angstroms away, but already all the crystal structures have a large degree of uncertainty. So what does that mean? I think it's fine.
Yeah. Yes, I guess androgen receptor was one of the systems that was a little bit tricky in some of the combinations of solvents. So what we find is that across all 3 solvent mixtures, the active site, which is in the center here, this is the portion of androgen receptor that binds hormones. It was the site with the highest total occupancy. Androgen receptor also has 2 known allosteric sites where ligands can bind and act as inhibitors. What we find is that for the simulations of the probes done individually, these are the next 2 highest ranked sites, as well as for the combinations of the pairs of solvents. However, when we run the solvents in triplets, we find that some of the other easily desolvated sites on the protein surface actually end up being ranked equivalently to the known allosteric sites. So for example, the site that says 30 here, that's a crystal packing interface. So that's a site that's known to be easily desolvated, but isn't necessarily a site that would truly bind a ligand and cause a change in the protein's activity. And what we believe this is due to is, in general, this is a lower overall number of simulations. So you're doing 20 simulations compared to 50 or 60 for the solo simulations. So you're having a lesser degree of sampling there. So potentially when you're running these solvents in combination, you could use either some sort of enhanced sampling method or longer simulations to account for that. So in summary, from our automated tool, we found that we can successfully identify binding sites. And then as far as the different setup procedures, again, it goes back to what you're interested in getting out. So if you are interested in identifying the binding sites, we find that any of the solvent mixtures give similar results. If you're interested in identifying all of the potential local interactions, the combined solvents tend to give a little bit poorer predictions than if you're running each solvent individually, because you don't have that competition between solvents. And then the last thing I'm going to talk about is, once we've done these simulations, we're interested in using them in a prospective way. So can we actually screen for potential new inhibitors? So we're interested in making what are called Pharmacophore models. So I don't know if everyone's familiar with this, but essentially it would be, if you have some ligand binding site, it'll be a map of the interactions that are occurring within the binding site. So these are typically represented as spheres. So you just need a center and a radius for each of your Pharmacophore features, which are the things that are making up your model. You can then screen for ligands that would fit this. So for example, if you have hydrophobic interactions in some site, or aromatic or hydrogen bonding interactions, you can screen to see how well different ligands satisfy your Pharmacophore model. So again, to generate these models from our data, we take our simulations where we've allowed the probe in the water to sample for binding to the protein surface. We count up at each grid point how often each of the probes are there. So we would repeat this process for each individual probe that we've done a simulation on. This gives you an occupancy value at each of these grid points. And typically what we do is to get rid of the low occupancy grid points. So we're looking at the high occupancy regions, and this will give you an occupancy for each of these points. Once we have these clusters, we want to identify and turn them into Pharmacophore features. So in this case, I've again used the dbScan clustering algorithm. In this case, we're using a smaller cutoff, so we're identifying grid points that are directly connected. To represent our Pharmacophore features, we take the highest occupancy point as the center, and then to calculate the radius, we take the RMSD of each of these points to the center, and that becomes the Pharmacophore radius. So it's represented as some sphere with the center and radius given from our data. So we've done this Pharmacophore feature generation procedure for each of the probes. In some cases, you'll have interactions that are made by different probe types that are occurring within the same regions. So in cases where these are overlapping, we want to identify or consolidate the features into a single feature that represents the different interactions that are taking place. So you can imagine if you have a site on the protein surface that is making hydrophobic interactions from different probes or aromatic interactions that are mapped by different probes. We test to see if these are within a specific cutoff distance. So in this case, we're looking to see if the centers are less than 2.5 angstroms. So this would be less than the width of a pyrimidine. In that case, we say that they should be represented by a joint feature. We calculate the average of all of these points. That becomes the center. And then again, the RMSD is the radius is the RMSD of all of these points to this center. And that gives you a joint feature encompassing the two different interaction types. In other cases, you might have, for example, hydrophobic and aromatic interactions that are slightly overlapping, but would be better represented as different pharmacophore features. So we've used basically anything that would have greater than this 2.5 angstrom cutoff. So if the centers were separated by 3 angstroms, we would say that those would be better represented by different features. So as a test system, we use the simulations that we had done of ABLE. So again, at high sigma values, we identify the active site. The allosteric site is the top ranked sites. In this case, we're focusing on the active site region. And if we take the sort of the moderate occupancy, that shows us the full extent of interactions that are occurring. And so what we do is we take the site we're interested in. We're going to take each of the grid points within that site for all of the different interaction types. So for example, pyrimidine or acetonitrile will show us the aromatic and hydrophobic interactions, or from isopropyl alcohol, we would get hydrogen bonding interactions. We use our set of scripts to turn these into Pharmacophore features, or a Pharmacophore model, which is converted into a form that could be used for the program Mo, which is a drug design software. So we used, again, Pharmacophore models from our MixMD simulations to do screening of our with our Pharmacophore models. We took known actives from the protein data bank. So ABLE kinase has multiple conformational states it can have. In this case, our simulations were started from the DFG out conformation. So we looked for crystal structures of ligands in the PDB that had or that bound to that conformation. That gave us 13 unique ligands. For the set of inactives, we used the DUD-E ABLE kinase decoy set. So DUD is a directory of useful decoys. It's a set of decoy compounds that could be used in virtual screening. That gave us about 10,000 compounds that we had for inactives. In total, the Pharmacophore model I had here has 13 possible features. And so what we do in Mo is you can adjust the stringency of your model, so either allowing partial matches of these features, so matching 10, 11, 12 of the features out of 13, or you can use a multiplier that increases the radii of your Pharmacophore features. So we initially tested 10 to 13 of the features, so matching any of the 10 to 13, and we found that was too specific. We didn't get any hits. So what that means is that it's essentially none of the ligands could satisfy all of the features at once. So reducing this to 6 to 9 features, we found that we did get a number of compounds that satisfied our Pharmacophore model. So what I'm showing you here, the percent of active compounds that fit the Pharmacophore model compared to the percent of inactive compounds. And then they're colored according to the number of features that they hit, or the multiplier that we had to use for that model. So you can see that some of the very stringent models, so using, for example, 1x RMSD for the radii and matching 9 of the features, we do have good specificity. We are picking up primarily active compounds relative to inactive compounds, but because it's so stringent, you're picking up few compounds overall. As you reduce the stringency of your model, you start to pick up more active compounds, and then once you get to matching fewer of the Pharmacophore features with larger multipliers to radii, that becomes a little bit too unstringent in that you hit a large number of compounds.
So this is ROC curve.
Huh? Yeah.
Question.
Mm-hmm.
You have only about 10 positive set,
Mm-hmm.
10,000 negative set. If in one setting, you correctly predict all the 10 positive set, you also predict 100 negative set.
Mm-hmm.
Then 90% of your prediction is wrong, but you will have a ROC curve on the upper left of your.
Yeah, so I guess this is just the typical way that they show them in
This is not a typical
for
case.
I guess for
For unbalanced data, usually people either use Matthews correlation coefficient or use precision recall curve, because ROC curve is known to be known to not perform well in unbalanced data set.
Yeah, that would be definitely something. If we were interested in doing a more in-depth analysis, then we could use some of those. I guess that's one of the hard parts when you're screening for sets of compounds, is you know that very few of them are actually going to hit. I guess that's kind of part of what happens when you're doing Pharmacophore models, is that you're going to have fairly low hit rates. Not all of the compounds are going to work.
So you want to say that you use ROC curve because it doesn't look that ugly if you compare to precision recall curve.
I guess I haven't looked at those curves, so I don't know what they'd look like. But I guess these are the graphs I have for this data. But so essentially, we do have our models are predicting that the active compounds do satisfy the model, a greater proportion of those relative to the inactive compounds. But this could potentially be improved. So we could look at taking our Pharmacophore models. In our screening, we've matched any of the Pharmacophore features, and that would be considered a hit, because we were kind of looking at the most fair test of our method. If you had domain knowledge, for example, if you knew that specific interactions were characteristics of inhibitors, you could preferentially select those Pharmacophore features, or as well as possibly ranking them by occupancy. For example, you might use high occupancy features and make those required, or low occupancy features and have those optional, which might help to bias your compounds towards things that would be inhibitors. Could also potentially integrate some of the shape information from these maps. So typically we represent these as generic spheres, but incorporating some more complex shape information might help you to get some greater specificity from this. So that was what I had. We have kind of a fairly small group now in the Carlson lab, but we've had several previous students that have worked on this project. Doing the simulations for the MixMD Probeview calculations, I had a PharmD student and a rotation student that did some of the simulations, and then we've been funded by several different groups. So, thank you.
So MixMD is for ligand binding site prediction and for virtual screening.
Yeah, so within a binding site, mapping out the interaction. So we're sort of just now starting to look for virtual screening.
So actually MD is not the most widely used method for ligand binding site prediction. So there are 3 other ways: geometry-based method such as concavity, template-based methods such as cofactor or find site, and machine learning-based methods such as coach. So have you compared MixMD with other methods not based on simulation and see what's the performance?
We haven't yet. I guess that might be potentially one of his projects in the future. But yeah, we've primarily focused. So I guess kind of the thinking in our lab is that some of these sites, for example, allosteric sites, might not be accessible in apocrystal structures. So allowing the flexibility that you get in the molecular dynamics simulations is really important.
Who knows? So maybe geometry-based method, if you assume a rigid body, but like template-based method, if you could find another template that has allosteric, but ligand binding allosteric site, it could still potentially hit it, right? And also, I think machine learning-based methods, they might also have their own way to go around this problem. So I could understand this is very decent research, but if there's no comparison with if other popular method in the field, is uncomfortable.
Yeah, so we've compared to FTMap, but we haven't done some of the other binding site prediction methods yet.
If I might inject here. Okay, now I'm going to put my bias on this, which is primarily, I spent my career in the pharmaceutical industry. The power behind this is you're going out and taking probes, okay? specific types of chemicals. And you're seeing where are the hot spots for these millimolar type interactions. So when you see an interaction this way where it does light up a hot spot, remember, millimolar compounds are hitting that, not nanomolar compounds. So mapping entire sites and all that stuff for me, as somebody interested in small molecule discovery, is actually not very useful. What I want to do is find out where's that hot spot that I can focus in that really likes even really lousy compounds, millimolar type of binding, so that I can take the small molecule expertise, focus there with something that is usually small, generally not terribly lipophilic and that kind of a thing, so I can apply those tools to really small systems that target that area that really was highlighted using actually lousy types of compounds for binding. So that's where, in my opinion, this really has the power.
I agree, but you still need to compare to something that is already established in the field. Right?
There isn't any, actually.
Of course, there
If
is.
you're measuring template-based things and other stuff like that, that's different. You're trying to find some big spot of some sort of general shape that kind of maybe sort of fits. The power here is highlighting where's the hot spot. Where is the sweet spot to go after and attack in a drug discovery process, as opposed to finding out this great big, huge, long, open cleft that you can find by inspection if you have crystal structure. Okay, it's really easy to do, but you need to find, you want to find the smaller areas, not the great big ones, because most of these things, when they register, you'll get 4, 5 peptides on either side of the active or the business district of this thing sliding in. That's where you kind of get your specificity and all these other things like this. But things of that size aren't any useful except in terms of, say, tools or something like this, something to cut in an assay or something along those lines. This is coming in much more from a drug discovery, small molecule point of view. Hence, where's the hot spot? What kind of interactions are you seeing at that hot spot that I can then take and find and go to a database and see what's going on?
I agree with all your points. It's just that there's already machine learning based methods.
Yeah, but it's apples and oranges. It's apples and oranges. You're finding a cleft. I mean, it's obviously, you can see here when you compare it to crystal structure, it's finding the right places. But, you know, comparing a template 2D based method, et cetera, or something like this, I don't see the point.
Have you run and compare, try yourself?
No.
If there's no data, then there's no way to argue.
I said it's still apples and oranges in my mind, but we agree to disagree.
Are there any other questions? Okay, I think we're at the hour, so thank you.